done besides the
Yeah.
robust scheduling stuff.
Yeah, thank you.
Too.
Thank you very much for coming. The people who stick to the last talk, they're really here for the science. Right. So thank you for sticking around. This is the last talk. I'm sure that you're all tired. I'll try to keep it on the light side. Simple theorems, pictures, and such. Like poisoning. Okay. So so the talk is really about adversaries versus machine learning, and you might have an awesome model that can in isolation without any interaction with the adversaries can answer very well, right? It might say, is this topic really important? And it comes up with very nice answer about seems to be pretty good workshop.
Your fire is ready.
Yeah. Okay.
Yeah,
And then the adversary comes and tries to change this into something that is a little bit different, right? And then the answer, but just a little bit changing the sentence, just putting a not in it, then suddenly it says, well, it may be considered less important by some people, right? And then it gives a huge list of why it is considered less important. Okay. So.
And you chose not to include that.
Yeah, well, it was just too long, and then maybe, yeah. maybe, yeah, I skip it for. Okay. So basically, when the adversary comes into the picture, they are usually grouped into two categories. Okay, either we have a training time attack or the test time attack, and I'm going to briefly explain what they are and what I'm going to talk about today. The test time attacks are very popularized. We have seen a lot of examples about them. So a machine learning pipeline is usually something like this. We have the data, we feed it into a learner, it gives us a model, we give a test example, this is a workshop, what is a workshop? And it gives the right answer. It is very nice equations, divergence, entropy. So it should be about information theory, good? Something like that, right? Okay. Now, there is when you have an adversary, in the test time attack, the adversary adds a little bit of noise such that the answer changes. Okay, so the adversary has access to the test point, and then it adds some sort of noise, and then suddenly it becomes another program, which is adversary approaches in machine learning, which is a completely different program with a different banner, okay, from Simon's. So that is what the adversary wants to do. Okay, so that is a test time attack. I'm not going to talk about it today. So the goal is to have low accuracy. What I'm going to talk about today is a training time attack. The goal is the same. The adversary wants to confuse the model. It wants to make sure that you make a mistake by controlling the model. But it doesn't have access to the model. So what does it do? It's going to poison the training data. It changes a few points from the training data. Then the learner is going to get that poisonous data points. And the model is going to change a little bit. And the goal is that this model on this data is going to predict something that is not correct. That's the goal of the training time attack. And these attacks surprisingly appear in large-scale industrial applications, because if you have a huge amount of data, you can never check whether you collected this huge amount of data. You cannot check individually whether they're good or not. And some malicious players can actually plant very bad data so that you make a mistake on a particular data point. Okay, so I hope that the distinction is clear between test time attack and the training time attack.
Looks like
We're waiting for you to ask that question.
making a pour over. That's what I thought.
That was a big grinder.
I thought it was
Coffee or meat?
That's what I said, coffee.
Or
Let it go.
maybe you're putting coffee with the meat. The meat.
Beans, yeah.
You're putting the coffee.
It's a poisonous coffee.
I have a more serious question.
I'm afraid. Okay.
Okay, so this is like a bizarre because unless you attack a certain number of those samples, first, if I was a very large data curator, like a power grid operator, maybe you can't come in and do this. That's what in distributed setting I can see this happen, but you have to attack a certain number of times. So presumably you're going to tell us all that stuff, right?
I'm hoping, yes. The point is exactly answering that question. So what we're going to talk about is what is called the instance targeted data point setting. What does it mean? I have a given an instance x, y. So that's a data point. It can be like this particular data point. The adversary makes changes to the data set so that the learner's output model gives a wrong prediction. So the label from green flips to a red one. Okay.
Just to plug in, we have been doing this work with IARPA where they want to know if you have a backdoor. So imagine you sell the model, and this is a sort of not really poison data, but you have Trojan data. So you have learned your model on something that gives you a backdoor.
There is also, it is very well. It is also related to what is called the backdoor attack.
Yes, which
Right.
are, yeah, which are pretty.
That's
They happen in circuits and stuff.
and if you have another target, then the adversary is going to change a different set of training data so that the prediction is going to be different. So to be more precise, what we have is a set of classifiers. It is called the concept class or the hypothesis class. It can be the set of linear classifiers or neural nets over domain X. These are the data points. So we call every pair of data point label as an example. And we have a training set S of n many examples and another test example XY that are drawn from the same distribution, unknown distribution. An adversary may replace some of the examples in S with arbitrary examples of its choice. And the goal of the learner is to design a mapping that maps every set S to a classifier H, such that the probability of error is minimal, even when it is exposed to malicious data points, poisonous. Right? So that's the goal. Now, to give a concrete but a simple example, let's consider the set of classifiers over a surface, two-dimensional space. They're all linear classifiers. Right? And so this is the training data sampled from a distribution. Just by eyeballing, I think we can say where the classifier should be, right? This is the classifier that is realized. We are going to talk, most of the talk is going to be about the realizable setting, meaning that there is a classifier such that the error is 0. Okay. And then I'm going to draw another data point X from the same distribution. If you look at it, I think you can guess what the label should be, right? Should be negative. Let's assume that there is going to be an adversary that can change at most 4 data points. All right. And what the adversary is going to do is that the goal of the adversary is to make sure that you're going to make a mistake here, right, on this data point. So it's going to change those four, the label of those 4 data points. And suddenly there's going to be another hypothesis from the class that is also realizable, but the prediction is going to be different from the actual prediction, correct prediction, right? So the adversary is successful in doing that. Good. Okay, so before talking about what we have done, let me actually say what others did. So the problem, one of the first studies was done by Steinhardt that they look at data poisoning attacks and try to understand when we can have algorithms that certifiably obtain unexpected low risk. So certification in this context means that even if I change a few data points, you can certify when you predict that the label is plus or minus, you can certify that the label is not going to change, even if I change these many data points. It doesn't mean that the label is correct. It means that the label is not going to change. I certify that the prediction is robust. There were more recent work by Rosenfeld and Fazy that studied how to obtain certified models are under the instance targeted poisoning attacks. They were more interested in obtaining practical methods with very, very good heuristics. Some of the results they had were, in real data sets, they were pretty good. And our work, or the way that I got interested, is really by looking at these papers. But what we try to do today is, try to understand, analyze learnability in these contexts. Under what conditions we can learn rigorously. Okay. I should also say that Bloom and company, they also have a work that they looked at the instance targeted learning, but they focus on what is called the clean label attacks, which is a very, very interesting type of attacks. What they mean is that I'm going to give you data points with correct labels, not the ones that I showed that you change the labels. They're correct. But what they're doing is that changing the distribution. And then by changing the distribution, suddenly the classifier is going to change and you're going to make a mistake.
Oh, if you don't change the labels, then you're changing the features, no?
No. Here, all the data points are correctly classified by the original classifier. But you go very close to the boundaries and put a lot of data points in some particular point, and then you tilt. Yes, that's the advantage. Okay. So in the first part is 2 theorems. In the first part, I'm going to talk about when is learning possible, and this is a work with G and Mohammed. And in the second part, I'm going to briefly talk about what is the optimal risk that we can obtain. And this is a work by Steve, Mohammed, Idan, and Shai. Okay. So when I say when learning is possible, I have to tell you what do I mean by learning. And here we're going to look at a very classical setting, which is called the pack learning. I have a domain X. These are the set of images. I have a concept class H. Learning is nothing but a distribution D unknown over the pair, right, of the domain and the labels. And we say that the concept class H is pack learnable if there exists a learning algorithm with the following property. That for any distribution D and any number epsilon delta between 0 and 1, when we run the algorithm on n data points, that depends on epsilon and delta, with probability 1 minus delta, the risk is going to be at most epsilon. What is the risk? It is a 0-1 risk. The probability of error, the learning algorithm, when it gets the training set S on a new data point X, it incorrectly predicts. Okay, so this probability of error, it should be less than epsilon. This is the pack learning framework. And what we would like to understand is that when we have data poisoning, under what condition pack learning is possible. So most of the talk about it is going to be about realizable setting. At the very end, I'm going to talk about the agnostic setting, which is much more complicated actually. Okay. So here, as you said, so we are going to define what is the eta ball of S is going to be the set of samples that we obtain by replacing at most eta fraction of the examples in the training data. That's the playground of the adversary. The adversary can change eta fraction of the data. The learner goal boils down to minimize the adversarial risk, which is defined as the probability that if there exists a sample S prime in this eta ball, such that you replace S with S prime, it prompts the wrong answer. Because if such a set S prime exists, the adversary is going to use it, and you're going to have a wrong answer. We want to minimize this probability. That's the risk. And this is a definition that captures the adversaries that even know what is a test point X and Y. And this is why this is called targeted data poisoning. The adversary knows the target based on the target it wants to make sure that it knows. Okay. So let's consider a weak adversary. What do we mean by a weak adversary? Is an adversary that knows the rule you're using, but doesn't have access to the randomness that you're using. All right. So you can use a randomized algorithm, and the adversary doesn't know what is the randomness that you use. And it's going to be very critical for this reason. So what we show, yes. The realization. It doesn't know what, yeah. So let's see what it, right. So the first result is the following. In this weak adversary, if the fraction of the data points that the adversary changes is sublinear, then pack learning is possible, and not only possible, proper pack learning is possible, meaning that you're going to return a hypothesis from the class. And the idea is by using subsample. So how does it work? Let's go to the next one. We know that the assumption is that the original problem was learnable, pack learning, okay? With these many samples, in order to achieve epsilon delta pack learning guarantee, we are going to upsample. How? We're going to sample the minimum number n such that this fraction is at least the square of what was before pack learning. So we sample more data points. And now we're going to subsample. Why? The adversary is going to choose a few samples and change them, right? Because the adversary doesn't know the randomness that we're using, we can subsample randomly from these points. So how many samples? These many samples. And these many samples is exactly this number here. And the reasons are twofold. First of all, this set of subsampled points is large enough that if you look at these subsample data points, it's a learn. You can learn it without a tag. You learn. If there was no tag and look at this subsample, you learn with the same guarantees of epsilon and delta. The second reason is that, so it's large enough, but it is small enough that it's not going to collide with the choice of the adversary. The probability that this set contains any contaminated data point is going to be small. So it is small, with very high probability, delta over 2 is not going to contain any data point that adversary changed. Hence, it's going to be packed learning. Okay. Good. But this strategy only works if the adversary doesn't know the randomness. If you have a strong adversary that knows the randomness, then we need to change the strategy. Okay. Basically, the the randomness of the learner should be fixed, and the adversary now changes a training set knowing the learner's randomness. And here, interestingly, we can show that again, as long as the number of examples that the adversary changes is sublinear in n, the problem is packed learning. But this time, it's going to be improper, meaning the classifier that we are going to output is not going to be one of the classifiers from the class, from the hypothesis class. And the reason is that what we are going to do is to use majority voting. So we are going to train a set of hypotheses and take the majority vote. And the majority vote of a set of hypotheses is not in general in class. Okay. The idea is simple. Like before, the original problem was learnable. We upsample. Now it's going to be a more complicated function. I'm not going to write it down. Okay. So it's a more complicated function of n sub h and epsilon delta. These many numbers we have to upsample, so more data points. And then we are going to partition. It's a deterministic partition. The adversary chooses a number of data points to change the labels. And the number of partition is going to be the square root of n times bn. This is the total number of partitions that we are going to have. So what happens is that, first of all, without any attack, if there was no attack, and we look at learning only from the samples from each partition, the problem is learnable with the same parameters. Okay, that's the first. That's the reason that we do these many partitions. The second is that we can show that there are not so many partitions that are contaminated. No matter what the adversary does, not so many of them are going to be contaminated.
I do this like packet erasures, like each partition is like a packet, and you're doing erasures from packet to the packet.
We take the majority vote.
Yeah, so it's
That's it. Because not so many of them are contaminated, the majority vote is going to be correct. Pigeonhole, majority vote. Sorry?
outside.
Yes.
So does adversary concentrate the information in particular partition?
It doesn't matter how it concentrates. It can do anything. Because there's these many number of partitions, it cannot contaminate all of them.
That means the number of partitions is more than the amount of samples the adversary can contaminate.
So this is exactly the number of partitions here, and the number of contamination is bn. The square root of n times bn. It's here. So it's going to be bn is sublinear in n. The square root is going to be sublinear in n. Right? So not all of them are going to be contaminated. Okay. The converse is also true. That suddenly, if you have a linear fraction, even 1% or 0.1% or any linear fraction contaminated by the adversary, packed learning is not possible. Right? So there is a phase transition here. And actually, there is a simple example to show that. Let's assume that the data points are only on these two rings. Okay. So it's uniform. So this is a three-dimensional ball, and the data is going to be concentrated on two rings with the equal probability. And if I want, and the adversary wants to change the label of this point, then it's going to place is going to replace eta half of the points in this ring, eta half of the points of this ring. Originally, it was possible to, with error 0, to classify. Now a classifier that has error 0 is going to be tilted, and you can push the error to 1 in this case. Yes.
So just so I understand, like in the previous sort of the good setting. So even if it's like you can poison n over log and log n, that's still
Yeah.
It doesn't affect the delta. Is like my question.
It is possible. Yeah. So yeah, it is possible. The number of upsampling depends on delta.
Oh.
This is kind of similar to, still remember, information-theoretic crypto, there was this notion of privacy implication.
It's very similar to that. And the people,
Okay.
Muhammad, who is the one of the co-authors, is a cryptographer.
Okay.
Very good. Yeah. Okay. Good. So the way that I would like to think about this problem is as follows: that learning on the poisoning is the following. In general, we have a set of points. Some of them are good. If you train on those data points, you get a very good model. Some of the data points are bad. If you train on them, the model that you get is not going to be very good. There are some data points that are originally good, but they're vulnerable. They're very close to the bad ones. And these are the ones that the adversary can flip and make them bad. All right? So learning under poisoning is possible if, as you collect more and more data, the collection of vulnerable and bad points becomes smaller and smaller, respectively.
There's an assumption. You're assuming that the upsampling will, you can always upsample more than your adversary can hurt you.
Right.
Yeah, these
I mean, once
are
I'm inside the control room of the grid, I can.
very good. So the assumption is that in the pack learning, right? So the pack learning is you give me how many data points, and then I give epsilon delta. I give you how many data points it is under this framework. You might say, well, you cannot get more than 10,000 data points. That's a different framework, and yeah, the results are these are more asymptotic.
Yeah, or it suggests you should train with smaller, so you have this bag of tricks to be more robust.
Yeah. So partitioning, and voting is very crucial here.
You just need an upper bound though on the amount of poisoning.
Right.
Yeah. Yeah. Should not be more than this.
Yeah, so that's like a resource constraint on the adversary. Maybe.
Yeah, it is. I mean, if you want to learn.
Sorry, I might have missed it, but when you partition, do you just need one single point in order to poison the whole partition, or?
Yes, let's say that yeah. If there is a one single point, but you don't know which partition
Right.
is poison, is poison, right? So you train on all the partitions. Some of them are not good, but the majority vote will take care of it.
Actually, no question. So in the first case, you have like you need to sample n squared examples from like the way literature. That means that actually you need to learn n more learners. Like in order to find the best learner, you need to learn them, right? You need to perform some optimization, right? To find the best learner. Without poisoning, you would have just you need to optimize. To find the best learner, you should perform one optimization.
Good. So when you do the upsampling,
Yeah.
in the first one that the adversary didn't know about your randomness, you still need one because you subsample that after that. In the second one, that's correct. Each submodel you have to learn. Yes, that's applying to
Is
K.
it like a lower bound on the number of? Do you have some lower bound?
Yeah, we showed that there is a phase transition. There's a very short phase transition. Either sublinear fraction or poisoned, you learn. If it is a linear fraction, you cannot learn in general. Very good. Now, let me briefly talk about the second part, because this just, in the first part, we just scratched the surface. What, whether learning is possible or not, we didn't talk about, what is the risk? What is the optimum risk? Okay. And that is the second part of the talk. So just to recall briefly, H is a concept class. Eta is a number between 0 and 1. That's a fraction, right, of the data points that you can poison. And we can define the optimal eta adversarial risk with respect to the concept class as the following quantity. So just forget about the inf. If you have a learner, that's going to be the risk of the learner under the hardest distribution, right? Without the inf. You have one learner, what is the risk under the hardest distribution? And then you minimize over all possible learners. That's the optimum adversarial risk. And then what we can show is that the optimal adversarial risk is going to be eta times the VC dimension. And this is typed. There is an upper and lower bound that match. So that's a crisp characterization of the risk in the realizable case. The idea is very simple. It's exactly like before. I just put it in. You have a question, I have 5 minutes or both.
Five.
Yeah, we're done.
Yeah.
I realized that my slides are not very complicated, so I put something that is a little bit more complicated. But then I realized it is as what we had before. It's the same idea, partition and vote, but it's a more careful analysis of partition and vote. This is the number of partition. This is the number of data points in each partition. You train, and then you take the majority vote. And that is how we get the result. Right? Now, for the realizable case, we understand almost everything. For the agnostic case, it becomes much more complicated. So in the agnostic case, what we have is that now there is no hypothesis that achieves error 0. What we are doing is that we compete with the best hypothesis in class, right? And that is the optimum risk. So in the agnostic case, what we can show is that the risk, so there exists a deterministic learner whose risk is going to be C times opt plus eta times the VC dimension. This is what we had before. This is the opt that we are competing against. The issue with this bound is that C is more than 1. In the agnostic setting, we usually want C to be 1. So that this is opt plus something. But then suddenly we get the best result that we get is C times that. It's not very satisfying. And it turns out that at least for deterministic setting, it is unavoidable. C should be at least 2. And let me finish with why. So everything that I showed you was about the upper bound. Let me show something about the lower bound, which is a very simple statistical question that you might.
I have a question. Opt is obviously probability of error, bounded between 0 and 1, and then you're adding BC dimensions could be very large. Eta is a fraction, but still.
Eta can be a very, very small number. It can even go to 0.
Eta is the fraction of what you do.
Eta times n is a fraction. Eta is a number between 0 and 1.
Yeah.
No, eta is here.
But then you want eta to scale at least 1 over BC?
Yeah, so the bound cannot be better than opt plus this. Okay, just to be clear, this is the best you can get. The unsatisfactory aspect of our bound is that this C is actually more than one. And for deterministic cases, it should be at least 2. Now let me say why. And it is a very funny question that boils into finding the conflicts. So let's assume that you have 2 hypotheses, H1 and H2, only 2, that they differ on the prediction on a single point X. And our distribution is only supported on X and 0 and X and Y. These are the labels. All right, 1 data point. I have 2 hypotheses that at this data point, some say this is 0, some say it's 1. The whole thing is basically determined by this probability that Y is equal to 0. So let's call this P. I have just 2 data, 2. Okay. Here's the thing. The adversary chooses P and flips n plus 1 points. If you knew P, right, what is the best strategy that you can, okay, it flips n plus 1 coins, tests you on the, right? If you know P, you're going to say, well, this is going to be heads, the probability P, right? The probability P, you're going to say heads, the probability 1 is P. You don't know P, that's the issue. You see the realizations, and then you're going to estimate P. Once you estimate P, you're going to say, well, I think this is heads with this probability, tails with that probability. All right. So that's a coin flipping that we have seen actually in the morning. Now, what the adversary does is also change a few data fractions. This is what you really see. And now, you want to understand how you want to predict on the test. What you can show is that this is your prediction, this is the optimum, and you can make it very close to 1. This 1/2 is exactly that 2 that you saw in the previous slide for deterministic. Right? So this only works for deterministic predictions. These are arguments. If you have a randomized predictor, this argument doesn't work. And we don't know how to fix it. Let me skip the proper versus improper. We have some results for the proper learning. Maybe the open questions. We actually don't have a characterization for proper. We only know it for linear classifiers. And then we don't have a characterization for the randomized agnostic learning. What should be this factor C? Is it really unavoidable or not? For deterministic cases, we know that it is unavoidable. So maybe if you have a randomized policy, you can get around it. Right? Okay, thank you very much.
So we're at -2. We may as well make it T-3 and have at least one question from the audience. We will pass. Yes.
Can you go back?
Oh. Let me go back. Yeah, okay. Which one?
To the coins?
To the points.
Sorry, I think this is a silly question, but why does that expression at the bottom not depend on eta?
That's a very good, because P is chosen by the adversary, and the adversary knows what is eta. How many data points the adversary can change. Based on that, the adversary is going to choose P. All right. And that is, and the fact is that you can always bring it to 1/2. Once you know, okay, this is your power, these many data points you can change. And now you're going to select P based on this knowledge. And then you can make sure that if the learner uses a deterministic rule, the regret is going to be 1/2. But yeah, that's a sharp, I had to add it, that's a sharp observation. Should have said that P is chosen with the knowledge of eta.
It's great to have a sharp observation. Sharp. Any other sharp observations, questions? Yes, Sarah.
Okay.
This Chuck, I'm just trying to think about, can you
Soft
soften
is also
the
okay.
certification to what? What did you say?
Soft is also okay if you have a
No,
soft
sure.
You
observation.
need blunt.
Butter and lime
You
observation.
need blunt, not soft.
Observation. No, it's not observation. I'm just trying to get a sense of whether you soften the certifiability in some sense.
I didn't actually talk about certification. It turns out that the same condition that I said, sublinear, linear, also applies to certification.
Yeah,
You
but
can
I'm
certify
saying-
the answer. So if the adversary changes a sublinear number of data points, you can certify that what you're saying is not going to change with these many flips.
Yeah, but now I'm just trying to see the question that Peter posed. Somebody comes and says, I have this, can I test and see if they did the right thing and they're really give me a reasonable certification, or should I trust, like,
Yeah. So as
so
long
I'm
as
trying to reverse the problem,
Very
just
good.
because we are in this IARPA thing now, we have to pass the model, we have to test the model.
I see. So you want to use
No,
this?
Yeah,
So
yeah.
as long as you know that the adversary cannot change more than a sublinear fraction, you can certify the answer. By partitioning and majority vote guarantees certification too.
Yeah, no, I understand. That's what I'm saying, what would I give guarantees that then it's not gonna pass? Yeah.
We have yet another.
So C in the upper bound, but do you have a value for that?
Oh yeah, we actually, I think in the paper we have some ridiculous value for that.
Because I was wondering whether you can actually show that you could get 2 by possibly reducing your voting to something like nearest neighbors, and then it becomes like an instance of covariant part. Like you basically just consider some sort of like a super sample, that effectively you're reducing your nearest neighbor.
Right. That's a very good point. We didn't do that. We were happy with 2. With 2 hypotheses.
No, I mean, I'm just saying like,
But-
get 2 in the achievability,
Yes.
like,
Yes, the constant is not 2 in the upper bound. It's C.
Right.
And I'm hiding what C is, of
Yeah.
course.
so I'm just saying like,
But
C
it might be.
could be
Okay, now I get what you're saying,
But
because
that's
for the,
fitting in some other ways.
you're using basically the base bound for,
Yeah.
that is, that's a
That's
good,
only for one nearest neighbors.
that's.
Sure, but
yeah.
I mean,
Maybe this.
voting is like a sequence of
Sure.
1 nearest neighbor type things, and then you do.
So this strategy where you partition and then train a bunch of different models in majority vote, like it does seem like that's adding a whole lot of effort to train a bunch of separate models.
Submodels, yes.
Even though you're even if it's only a few data that are poisoned. Do you think that's fundamental? Like there's no way around having to do that, or maybe there's some?
I don't know of any way. Yeah, I don't know of any way of doing that without majority vote.
Yeah, I'll just add the point of there's two main ways of doing private machine learning, and one is DPHD and the other is PETE, which is private. You aggregate, you partition your data, and then you have the vote, and then you train a model based off those votes, and so you get privacy after that, but you kind of get this for free.
Yeah. So I don't know of any other, like, unless you have submodels that many of them are good, and then you do the majority vote. That's why the proper learning, I think, is important. Like this is an improper learning. If you can get to a proper learner with that would be super cool.
Thanks to everybody. I mean, we couldn't have done it without you guys. Really want to thank